Hello students, welcome to my class. So in this video, I will be telling you all about metal hydride reduction, which is also another important topic under the unit reduction reactions. So what are metal hydrides? They usually have metals in them like lithium or boron or any other metal. The hydrides, they act as very good reducing agent. Two important examples that you're going to study here is one is lithium aluminum hydride and sodium borohydride. Two of them are very good reducing agents. So you will be studying about reductions using these metal hydride, what is a mechanism and how these metal hydrides can be prepared. So we will begin with lithium aluminum hydride, which is one of the most widely used reducing agent. And how is it prepared? It is prepared by the action of anhydrous aluminum chloride AlCl3 onto the paste of lithium hydride, and this reaction is done in the presence of THF or dry ether. Okay, THF is nothing but hot boiling ether. So why is lithium aluminum hydride used? Most commonly used as a reagent for to carry out reduction, maybe of ketone, carboxylic acid, ester, acid chloride, anhydrides, epoxides, nitriles, etc. And some of the examples are given. So if they ask you a reactant and a product, you should be able to write what type of reducing agent is used. Usually if these are carbonyl compounds or carboxylic acids or esters or acid chlorides, generally lithium aluminum hydride can reduce all of them into alcohols. So these are some of the examples. Here you can see hexanal, which is an aldehyde, is reduced to an alcohol. Same way here you can see that acid chloride is reduced to alcohol, and ketones, that is cyclobutanone, is reduced to cyclobutanol, which is an alcohol. Same way carboxylic acid is also reduced to alcohol. Other than that, azides, they are reduced to amines because azides are nitrogen containing species, and when hydrogen is added to them they become amines. And oximes are also reduced to amines. Nitriles can also be reduced to imines. So these are some of the important reduction reaction that is catalyzed by lithium aluminum hydride. Next, we will see how exactly is a mechanism of reduction using lithium aluminum hydride. So here in lithium aluminum hydride, actual part that is used for reduction is this AlH4 minus part. Okay, and Li plus part is there, but it is not of that importance. The AlH4 minus part has the hydride ion. So the complex hydride ion, it acts as a carrier of hydride ions, and all four hydrogen atoms of the lithium aluminum hydride, they are available for the transfer to carbonyl group. So let us take an example. We are taking a carbonyl group. You know that in carbonyl group there is C double bond O, and the pi electrons shift onto oxygen because of the higher electronegativity of oxygen. So there comes a minus charge on oxygen and plus charge on carbon, and that time what happens is one of the hydride ion, that is H minus, will come from AlH4 minus. One of the H will come out as H minus and come and attach onto this particular carbon. So we get CH. From where did this H come? It came from this AlH4 complex. One of the H came out as H minus and comes and attaches onto this carbon. What else is left? We have AlH3 plus part, correct, and oxygen has a minus charge on it, so that part will come and directly attaches itself onto the oxygen atom as a complex. Here you can see, and lithium is also there, so there will be a partial negative charge on this particular AlH3 complex, and H plus ion will have a partial positive charge on itself. Okay, so we get an intermediate like this. Now there are still three more hydride ions. So what we can do is we can make this molecule further reduction can be carried out. to three more ketonic groups. So all those groups, same mechanism continues. We have not written it, but same way mechanism continues. In all the three groups, what happens is that this pi bond shifts onto oxygen. Oxygen gets minus charge. Carbon gets a plus charge. One of the hydride, in every step, one hydride, one of the H minus will come and attaches onto the carbon, and the rest of the part is already there here. The rest, that is the oxygen of this group, will attach to the aluminium center. That is what happens. So by the end of the reaction, once all the three hydrides, since we have to remove three hydrides, we are taking three ketonic group, and this same reaction continues three more times, and finally what do we get? Four groups of because one, two, three, four, three plus one, four groups of this aldehyde is there. Four times Al minus Li plus, and this on hydrolysis will give you an alcohol. The alcohol group is obtained. So what is happening? The initial transfer of hydride to the carbonyl carbon and coordination of aluminium to oxygen generates a tetrahedral intermediate. Where does the hydride group go? To the carbon, and that is it, to the carbonyl carbon, that is this one. And coordination of aluminium, where is this aluminium center coordinated? It coordinates to the oxygen. Same way to these three ketones also same thing happens. The hydride ion from here will get transferred to the carbonyl carbon, and this oxygen of every ketone, all the three ketones will coordinate with this aluminium. So finally to the aluminium, four oxygens are attached from the four ketone groups. Okay, since there are no more active hydrides in this case, you can see once all the hydrides are transferred, there are no more active hydride. What happens? Last, the reaction cannot continue, so it will undergo hydrolysis, and you get the reduced product, that is alcohol. So this is the reaction mechanism. Next is reduction of carboxylic acid and its derivatives. So you know that lithium aluminum hydride has a capability to reduce carboxylic acid and its derivatives. So derivatives are esters, acid anhydride, acid chlorides, etc. All of them on reduction with in the presence of lithium aluminum hydride, you will get the corresponding alcohol. And aromatic anhydride, that is when they have aromatic ring, they will sometimes undergo not complete reduction, they can undergo only partial reduction. And the order of reactivity is acid chlorides are very reactive to reduction reactions compared to cyanide groups, CN groups, and last is the acid carboxylic acid groups. So these are some of the examples involving where carboxylic acid groups and its derivatives, they are reduced in the presence of lithium aluminum hydride, and you can see that all the products that are obtained are alcohol. So acid chlorides and all of its derivative, they yield alcohols in the presence of lithium aluminum hydride. So next we will be studying about the mechanics. So lithium aluminum hydride is one of those only few reagents which can which can reduce carboxylic acid. Usually reduction of carboxylic acid is not very easy. So lithium aluminum hydride can reduce this carboxylic acid to alcohol. So the mechanism of this reaction is still not very clear, but they're telling that what happens is, first there is a formation of the carboxylate ion, that is the lithium gets transferred here, hydrogen, the H plus ion goes out. So the lithium here takes the place of the H plus ion, so there is a formation of carboxylate ion. After that, it is followed by addition of hydride ion to the carbonyl group to give tetrahedral intermediate. So what they're doing is there is an addition of this hydride group ion to the carbonyl group that gets added over here to give this particular intermediate, that is tetrahedral intermediate, which further collapses to give aldehyde. Or and you know that once you get aldehyde, this can be further reduced to give alcohol. So that is how carboxylic acid group, it cannot directly be converted into an alcohol. First it is converted into an aldehyde, and then aldehyde is further reduced to give an alcohol. And reduction of Next is the reduction of diesters. Diesters, they are usually reduced to diols in the presence of lithium aluminum hydride. So here is an example of diethyl adipate. It is reduced to hexane 1,6 diol. Same way, sebacic acid is also reduced in the presence of lithium aluminum hydride to decane 1,10 diol. And many lithium aluminum hydride reduction of esters, acids, acid chlorides, they will never stop at intermediate the obtained, that is aldehyde or ketone. Usually when we are reducing esters, acids or acid chlorides, we will get an intermediate that will be an aldehyde of ketone, and we cannot stop at that stage. So final product that is obtained after the reduction of this acid and ketones will be alcohols. Finally, these esters, acids, acid chlorides, they will yield alcohols on reduction, because the intermediate, that is acid aldehydes and ketones that are obtained, cannot be, we cannot stop the reaction at that intermediate step. Complete reduction to alcohol will take place. So here is an example of reduction of an ester to in the presence of lithium aluminum hydride. So step number one, what happens is there is a migration of pi bond. It shifts onto oxygen as minus and carbon gets a partial positive charge. Then the hydride, one of the hydride ion from lithium aluminum hydride, H minus, will come and attach onto carbon. At the same time, the Li plus will go and attach over here, form a bond here, because there is a negative charge on oxygen. So the Li plus part from here will go and attach here. So here you can see now once again there is elimination of this group, that is OC2H5 will go out. Elimination of that particular group along with lithium takes place, that is LiOC2H5 is eliminated, and this minus charge on oxygen is shifted back as a double bond here. So what do we get? We get an aldehyde. Now this is the reaction intermediate that we have got on reduction of ester, but we cannot stop at this, because it has to further, aldehyde has to further undergo reduction to give an alcohol. So how does aldehyde reduction takes place? What happens once again here? Same step. There's a pi bond shift onto oxygen. Oxygen gets minus charge. Carbon here gets a plus charge. Since carbon gets a plus charge, one of the hydride ion from the second lithium aluminum hydride. So here you will require two molecules of lithium aluminum hydride to carry out this reduction. So the second lithium aluminum hydride molecule is taken. One of the hydride ion will attach onto the carbon. So it is attached over here, and to oxygen, oxygen, since it has a minus charge, the Li plus part will come and attach here. Okay, and next what else is left? AlH3 is left, correct, because Li plus got attached over here and hydride ion got attached to the carbon. Next, that AlH3 part will come and attach in the middle of oxygen and lithium, and in the last step what we are doing is we are doing hydrolysis of this particular intermediate to give an alcohol. We are adding H plus. Next, unsubstituted amides, they form primary amine, whereas N-substituted amines, they give secondary amines. So these are, you can see here, N-substituted amines, they give a secondary amine, and unsubstituted amides, they give primary amines. And the reduction of amides in the presence of lithium aluminum hydride, what will it give? It will give you an iminium ion intermediate, which after the reaction, once the reaction is complete, what do we get? We finally get an amide. So reduction, iminium ion intermediate is obtained, and once the reaction is complete, amide is further reduced to amine. So what do amides give on reduction? They give you amines having an iminium ion intermediate. So when the reaction is carried out at low temperature at around 70 degrees Celsius, amines amides can also be reduced to aldehydes, and the tetrahedral intermediate that is formed is more stable. So let us see the mechanism wherein the amides are reduced to amines. So here you can see this is a reaction mechanism of reduction of amides. We have taken an amide here, and there is a shift of this reaction mechanism is the same thing, that is there's a shift of the pi bond onto carbon oxygen gets minus and carbon gets a plus charge. Then the hydride ion will come and attach to the carbon here, and the lithium part will go and attach onto the oxygen. After that, what happens, the AlH3 part that is left will come and attach here in between two, because there is no bond formation, only because oxygen is having a negative charge and lithium is having a positive charge. There is a force of attraction that exists between these two atoms. Okay, and AlH3 will come and occupy this. So this you don't have to write it as a separate step, you can directly write from here to here. And then what happens, then there is a elimination of this group, that is this whole group Li plus and OAlH3 is eliminated off, it goes out as OAlH3 minus and Li plus. And nitrogen, you know that nitrogen has lone pair of electrons on itself, it donates that lone pair of electrons to carbon and forms a bond between carbon and nitrogen to give Nr2, and there is a positive charge on nitrogen saying that nitrogen is now electron deficient. Why is that? Because nitrogen donated its lone pair of electron to form bond with carbon. So this is nothing but your iminium ion. So previously they were telling there is a formation of an intermediate, that is the iminium ion, that is this one. Next, what happens in the next step, we are supposed to convert it into an amine. So we are taking our second molecule of lithium aluminium hydride, which gives another hydride ion. Now in order to remove this plus charge on nitrogen, this pi bond shifts back onto nitrogen. So carbon now has only three bonds, and the fourth bond is formed by, since it has only three bonds, carbon will be electron deficient. So one hydride ion is once again given by the second molecule of lithium aluminium hydride here, and you get an amine product. So this is a reaction mechanism in the reduction of amides. Next, that is about lithium aluminium hydride. Next, we are studying about reduction with sodium borohydride. Sodium borohydride is also another type of metal hydride that is used. It is mild and specific reducing agent, and it is much more selective compared to that of lithium aluminum hydride. And unlike lithium aluminum hydride, which reduced all the organic compound, almost all the organic compound, here sodium borohydrides are very selective in nature, so they reduce only aldehyde and ketone groups, and they cannot reduce acids, esters, or amine. And sodium borohydride, it is insoluble in ether, but it can dissolve in alcohol, and so you can carry out its reaction in alcohol medium, or it is only because it's insoluble in ether, you cannot carry it out in ether, but you can carry out the reaction in alcohol or aqueous medium, which you cannot do in lithium aluminum hydride, because they show very vigorous reaction in the presence of water, correct? But here in lithium aluminum hydride, you can do the reaction in the presence of water. So how is sodium borohydride prepared? Preparation of sodium borohydride. You are taking sodium hydride and making it react with trimethoxyborane. You get your sodium borohydride compound. Next is reaction mechanism involving sodium borohydride. Now, sodium borohydride also follows the similar reaction mechanism as you studied in lithium aluminium hydride. Here, the pi bond gets shifted onto oxygen. Oxygen gets a minus charge. Carbon gets a plus charge. Since carbon gets a plus charge, one of the hydride ion, that is H minus, is transferred to this carbon. So there is a H, one H forms a bond here, and rest of the part that is formed, that is BH3, will form a bond with the oxygen here, since oxygen has a minus charge. Okay, so here the minus actually indicates the minus charge on hydride ion, not on the entire compound. You have to understand that. That's why although we are writing minus here, it does not indicate that the charge is on the compound. It is indicating that there are hydride ions present, so there is minus charge here. Next, what happens, same way, you can, there are three hydride ions, so you can do reduction of three more ketones. So you are adding 1, 2 and 3 ketones. You need not show it in three different steps, but if you want it for your convenience, you can show it like this. One ketone is added. So as you keep on adding the ketone, the number of groups here increases, 2, 3, 4, and the number of hydride ions here will go on becoming less. So 3 became 2, 2 became 1, and then lastly we don't have any ion at all. Now we have only minus charge on boron. Finally, when you get a compound like this, what you will do? You will do hydrolysis and it will give you an alcohol. This is the mechanism. So in case if water and alcohol are not used as a solvent in the sodium borohydride reduction, this reduction can also be done in the presence of benzene by using a charge transfer catalyst such as quaternary ammonium salts or crown ethers. So here they have given you an example of reduction of ketone to alcohol. It's done in the presence of benzene by using quaternary ammonium salts. So these are some examples wherein one is in the reduction of aldehyde to give an alcohol in the presence of sodium borohydride. Here there is ketone reduction in the presence of sodium borohydride. It's reduced to alcohol. So these are some more examples for reduction with sodium borohydride and lithium aluminum hydride. So from these examples, you can clearly differentiate between lithium aluminum hydride and sodium borohydride. See, in this particular example, same compound is taken, and when it is reduced with lithium aluminum hydride, you can see that this aldehyde group is converted into alcohol. Along with that, this double bond is also reduced to single bond here. Okay, whereas in case of sodium borohydride, since it is very selective in nature, it only reduces this aldehyde to alcohol and the double bond is retained as such. Similarly, in this reaction also you can see when the same compound is taken, the reduction of in the presence of lithium aluminum hydride, only this in presence of lithium aluminum hydride along with this ketonic group, this group CO2 is also reduced to CH2OH. But whereas in presence of sodium borohydride, you can see that the CO2 group is retained as such, and only the ketonic group is reduced because sodium borohydride is very specific. It will reduce only aldehyde and ketone and no other bonds except for that. So these are some of the examples of lithium aluminum hydride and sodium borohydride as reducing agents. Next is the stereochemistry of reduction with lithium aluminum hydride. So stereochemistry tells us about how, what exactly type of product is obtained. Is it axial or equatorial? How are the groups arranged, etc. So it depends upon two factors, that is during reduction with lithium aluminum hydride, the stereochemistry depends upon two factors. One is stability of the product that is formed and steric hindrance to the reagent, that is when the reagent is attacking, how much steric hindrance is there, and the product that is formed, how much stable is that particular product. So we are studying stereochemistry in case of camphor. So you can see here in the case of camphor, we got on reduction with lithium aluminum hydride, we got an exo alcohol. And exo alcohols are usually obtained due to endo attack, whereas endo alcohols are obtained due to exo attack. So here you can see in this case, in this camphor, the H minus will attack from sterically hinder. What happens here in this case is that you can see that there is a dimethyl group that is present here in this particular camphor. This is called as a germinal dimethyl group. Because of this presence of germinal dimethyl group, it does not allow the hydride attack from the lithium aluminum hydride to take place from the exo site. Okay, so since exo attack cannot take place, there will be endo attack taking place, so yielding exo alcohol. If there is exo attack taking place, then you will get an endo alcohol. But here in this case, that is in case of normal camphor, because of the presence of germinal dimethyl group, it gives, you can see that two bulky groups, two dimethyl groups are present here. It gives hindrance for the reagent to give its hydride ion, because of which the reagent prefers, instead of exo attack, it actually had to do exo attack, but instead of that it will do endo attack because of the steric hindrance that is created here, and because of that we will get isobutylol, which is an exo alcohol. Okay, and if that group is absent, like in case of nor camphor, you can see there is no germinal dimethyl group, so now there is no hindrance for this lithium aluminum hydride to give its hydride ion. There is no any kind of steric hindrance here. So what happens? There is exo attack taking place here, and we will get an endo alcohol. What is the difference between an exo alcohol and endo alcohol? Only thing is, in case of exo, the OH will be on the top and H on the bottom. Here the H will be on the top and OH will be on the bottom. So usually reduction of camphor should actually give you an endo alcohol, but here in this case, because of the presence of germinal dimethyl group that creates steric hindrance, you get an exo alcohol instead of an endo alcohol. So that is about stereochemistry. Next, another example we are taking in case of cyclohexanones. So cyclohexanones which have considerable degree of steric hindrance near the carbonyl group will usually yield an axial alcohol, while those which do not have considerable degree of steric hindrance will give you an equatorial alcohol. Now you can see this is cis 3 methyl 4 tertiary butyl cyclohexanone. Okay, and there is a carbonyl group here, but you can see because of the presence of 3 methyl group here, there is a steric hindrance that is created to, so that if the reagent, that is lithium aluminum hydride, has to send its hydride ion, one hindrance is created here because of this 3 methyl group. Because of that, it yields an axial alcohol, because they are telling that when there is steric hindrance, we usually get the yield that is an axial alcohol, wherein OH will be present in axial position. Whereas here in this case, you can see there is no 3 methyl group, and hence there is no steric hindrance, and when there is no steric hindrance, you will get what? You will get an equatorial alcohol. So this is another example of how, because of steric hindrance, the product that is supposed to be got is altered. You get an axial alcohol whenever there's an steric hindrance, you usually end up getting axial alcohol, whereas you get an equatorial alcohol when there is no steric hindrance. And stereochemistry not just depends upon what type of compound, organic compound we are taking, it also depends upon what type of reagent we are taking. So they are telling that the stereochemistry changes of the product that is obtained also changes when you are using bulky reagent. Now you know that lithium aluminum hydride is not bulky. When 4 tertiary butyl cyclohexanones are reduced with just lithium hydrides or sodium borohydride, what do you get? You get an equatorial alcohol. When do you get an equatorial alcohol? When there is no steric hindrance involved, you will get an equatorial product. But when there is steric hindrance, you get an axial product. So lithium aluminum hydride or sodium borohydride, you know that they are very small groups, so they won't have, they are not bulky reagent, they are very light reagent. Whereas same if we substitute lithium aluminum hydride or sodium borohydride with some bulky reagent like tri-secondary butyl lithium borohydride, in same thing we are substituting it with a bulky reagent like tri-secondary butyl lithium borohydride. What do we get? For the previous reaction we will get an axial alcohol. Why? Because this time it's not the organic compound that is bulky, it is a reagent that is bulky, because of which, because of steric hindrance, because of the reagent, the product that is got is altered. So this is about how steric hindrance affects the product formation. So with this we have completed metal hydride reduction, and the next few topics will be discussed in the coming videos. So thank you for watching my class. Take care and bye.